So this sum of exponents is equal to 1. You double the income, you double consumption of each of the goods. The ratio of x1 star to x2 star is the same. If the exponent sum is large or smaller than 1, then only this ratio changes. So you shift your consumption. You double the income, so the consumer consumes less than, like if you double income, would consume more than twice x1 and less than twice x2, or the other way around, less than twice x1 and more than twice of x2. So this is this idea. Cobb-Douglas is homothetic. All Cobb-Douglas functions which have the sum of exponents equal to 1 is homothetic, but there are other utility functions. And sometimes this is very interesting because you know, so in macros sometimes you want this, that the ratio of consumption between the different goods is the same, independently of how much income you have, because then you know, like, you can give the guy more income, less income, the prices don't change, you know the ratio of consumption is always the same. So this is a nice property, and sometimes you want to have it. In micro, not so much, but in macro, it's sometimes homothetic references are useful. What else? I want to say something about. Okay, so Cobb-Douglas for me is like substitutes, complements. We can find these examples which are nice, but actually, well, they're a bit stylized, just very few examples fit this. Well, Cobb-Douglas is a utility function is actually is something which most of us have if we go shopping. So if you go shopping, you want to cook something or buy stuff for the week, and our utility is pretty similar to this one. All the goods we buy, you buy 10 different goods, and then you have here 1 over 10, 1 over 20, 1 over 100, 2. So this is very characteristic to how we go shopping. Namely, we buy many different goods, we have a certain proportion, so some goods we value much higher than others, which are more important than others. And if we miss one of the goods, if you want to cook something and you don't have onion, it's not very important, but then your dish is not the same. And your utility is 0, because you lack some ingredient, okay? So you buy many different goods, but if you miss one of them, you can do without it, but your utility is not very high because you need all the goods, all the different goods. So this is more or less the utility we have when we go shopping. So shopping is many different things in this relationship. And we buy some of them many because we like it more, it's a much higher utility, some of them less. Some of these goods which we like a lot are very expensive, so we still buy few of them. But this is very much what we do when we go shopping. And if we like one of them, bad. Okay. So this is relatively, I think, describes how we actuate, how we actually behave in reality. Okay, now that we have done the utility maximization with examples, we will have more examples in the chapter on general equilibrium. And then I will show you also, like if you put them together, general equilibrium, different people with different utility functions, how they interact in the market, then we see how this plays together. You put two guys with different utility functions in the market and you let them clear the economy, how this works. Now what we do is the next thing, I write down some properties of the moderation demand functions and the indirect utility function, which is all useful. And then we move on probably today to chapter 2, which is about uncertainty. So, properties of indirect utility function and machine moderation demands. Properties of VP and XPM. It's indirect utility function and moderation demands. Okay, so first for VPW, first property. Well, derivative of VPW with respect to W is larger or equal to 0. If I get more money, I'm happier, or at least as good. If I reach my bliss point, I get more money. Well, I don't spend extra money, but I save more. My utility probably also goes up. And similarly, if I take the derivative of VPW to PI, if I increase the price of one of the goods, then my indirect utility is going down. It can be equal to 0 if and only if, well, if and only if, let's see. It can be equal to 0, for example, if I'm not buying the good, If I'm not buying the good, I don't care about the price going up. Or if I'm having substitutes and I'm indifferent between the substitutes and I'm switching to another good, and again, my utility is not affected. Otherwise, it's always negative. As you can imagine, because getting more money or better off weekly and getting higher prices, you will weekly worse off. It's continuous in PW, which again is something useful sometimes, we need it, but one of the properties. So, nothing spectacular about it. It's quasi-convex in P. Quasi-convex is an analogous definition to quasi-concave, but for convex, it's quasi-convex in P. And this implies basically that the set, put it differently, PW V PW is smaller equal to V upper bar is convex, it's a convex set for any V upper bar. Again, a property which sometimes is useful. And it's homogeneous of degree 0 in PW, which means if I double all the prices and income, the consumer is as well off as before. So he gives the guy twice the prices, if I double his income, he has no, so indirect utility is the same. Usually if you increase prices, the consumer will change the consumption. So if he changes the consumption, he's actually better off. So if I give him twice the prices and twice the income, he can also sometimes get better.
On number 3, what is that? Set PW VPV
is smaller equal to V upper bar for any V is convex. So it's a convex set. These are properties, so they are useful. Some of them we will use later on. Some of them are just there for you. Sometimes maybe you will use them. Maybe in your master thesis you can write something theoretically about preferences. If not, but it's interesting to see how to get to characterize these functions better, to understand how they work. XPW, so Laurasian mod. Well, one XPW is homogeneous of degree 0 in PW, same idea. So if I increase our prices in W, the guy buys the same bundle. In PW, it satisfies Walras law. Which basically says if all but one market clear, or the last market clears, which implicitly said you can use to tell if one market clears, the second market clears, the third market clears, so once one market clears, all the others clear. And this implies that XPW times P is equal to W. So if I multiply the demand functions by P, you get again the income, not surprising, because before we had W is equal to XP. So if I calculate the optimal bundles the consumer consumes and plugs them back into the budget, multiply them with the prices, I should get W back. Otherwise I did a mistake. So some of these properties are either very simple or obvious, some of them we will see later on how useful they are. If preferences are convex, so U is quasi-concave. So then XPW is a convex set. And the convex set can be a point. So a point is trivially a convex set. So if you get a solution which is one number, one solution, 1 point, this is a convex set, so it's good. But the other way to get a convex set is with substitutes. If you put substitutes and get a correspondence, it's also a convex set. Okay? So we can also do substitutes, and those preferences have the same slope as the difference curve. You can get solutions at any point on the budget constraint equal to the difference curve, identical with the difference curve, is an optimal consumption point. In this case, you also have it's a convex set, because, well, you can choose 1 point, you get the other point, and this is a convex set. So correspondence. Good, then. If the preferences are strictly convex, then U is strictly quasi-concave, so then we still get a convex set, but now it's a singleton. Then XPW is a singleton, which is 1 point, and a singleton is trivially a convex set. Singleton. Some of these properties we use later on.
XPW is a single what? Okay.
It's a singleton.
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 Okay.
Singleton. Singleton.
What's a singleton, professor?
Point. One singleton is one single element. Okay, now since we have done utility maximization, the corresponding way, what we can also do sometimes is expenditure minimization. The expenditure minimization problem has to be well understood. So expenditure minimization problem, what we do is mean by the choice of x, p times x, subject to u of x being larger equal to u, so some fixed relative utility. With all the prices positive, and the utility we want to have u upper bar larger than a utility of 0. Okay, so once we have done utility maximization, the next thing is to do expenditure minimization, and this is what today most of the managers in companies or in the faculties have to do, is they have to minimize the expenditures. What a bad manager does is he forgets about this part here, because you can always cut cost. The lowest cost is when you reach 0, so you cut everything away. And clearly on the way to going down to 0, there's a point where you reach this limit. If you go below, you will mess up because people will be upset, and then you have low expenditures, but you don't reach any more this utility. So if you cut this, as you will see managers in companies doing this, usually it's a sign of a bad manager if there's a slim toilet paper. Because sometimes you can cut costs, but another time you increase costs, because then you can think about what people do. Okay, so this is very important. So you minimize expenditure, but subject to reaching a minimum utility level which is larger than 0, which is above the 0 consumption level. You do this, same thing as before, just now minimizing. So the lambda and the Lagrangian goes in the other direction, but I don't care. Because you approach this constraint from the other side now. What you get is a solution. And we will not do much about this expenditure minimization, so I will just tell you for completeness a bit what it's about, and then, because I want to relate it with utility maximization. So utility maximization and expenditure minimization give you the same solutions, and I will show you how. This is why I want to introduce briefly expenditure minimization. If you do this, you take demand functions, which are called Higgshian demand functions, and this muscular just continue to use the same expression as in the literature. Well, or correspondence, if it's not a function, and this is called Higgs. Sometimes it's also called compensated demand. compensated demand, since U is kept constant. So you compensate demand somehow by keeping U constant. You can get like the indirect utility function. There's an expenditure function. Which is put in these Hessian demand functions, which are called HPU. Hessian demand function, which depends on prices P, and the utility level U you keep constant, you want to reach. The expenditure function E of PU is plugging these Hessian demands back into the budget constraint. So P times H of P. And then you can see the properties of this is again in Mascolel, Winston Green, if you want to check it, MVG, propositions, 3 in 2, and 3 in 3. Now you can get a list of properties of EPU and HPU. Like we got for the indirect utility function and the variation demand functions, you get the same for these indirect utility functions. And now this is why I put it there. We want to relate it with the variation demand functions and with so Hessian and variation demand functions, and utility maximization is expenditure minimization. Okay, so what's the relationship? This is called duality. Relation between Hessian and variation demands or between you need to know, you can read my handwriting, you can read. Yeah, sometimes you ask them, the longer the class takes, the sloppier, because I'm getting tired, so the marginal productivity is decreasing. Same thing with, I think, because I'm sometimes speaking, if I'm not speaking clearly, you also ask me to repeat. Sometimes I'm going fast or mumbling.
So what is the relation between?
Between Hessian
Variation demand.
and variation demand.
Oh, okay.
Or between utility maximization and expenditure minimization. Yeah, so this will be going down. So also in each lecture is a decreasing productivity, and also until the end of November there's decreasing productivity overall, so there's a decline.
But what does it mean, Hessian?
So what we do is
It's a guy.
it's a name. X is a guy, it's an economist. What we do, we minimize P times X subject to this.
Okay.
We get the solution, which we call demand functions HPU, and we call them Hessian demand functions. It's just the optimal solution, which are evaluated at these prices, which you have here at the utility level district. Just the name.
When you write U bar, is that U is fixed?
It's fixed at this level.
Okay.
You select the utility level, whatever, then you want to reach at least this utility with the smallest expenditure. So what we do usually with the picture, just because the center. So utility maximization, what we do is fix the budget constraint. Try to reach the highest possible indifference curve. So there are many different curves. You maximize utility reaching the highest. What happens with expenditure mean? Expenditure mean. What we do is we have one utility level, U bar, and then what we try budget constraints, different budget constraints. We minimize the expenditure to get to this utility level. Minimize one, to this one. what we have price is fixed, but we choose which is the minimum level of W to reach this. Okay? Then you see what, somehow it's the same because we have a difference curve. If I put this in difference curve here, and this budget constraint here is the same ones, and we reach the same solution. Whether maximize utility or minimize expenditure, so there's a certain relationship. And this one is interesting, and this one is the one I want to explore a bit further.
Marcus, it's a singleton.
Singleton, yeah. Singleton is one point, one element in a set. A set with one element is called singleton.
Like that we said.
So first thing is relationship between this valuation and Hickson demands. And this comes from the following picture, which also so Annika may remember because I drew this in micro, so if I can draw it again. So what happens is, so if we change prices, there are basically two effects. One effect is always a substitution effect in the consumer's change of demand. Namely, if one price goes up, you buy less of the good which became more expensive, and more of the good which didn't change in price because relatively it's cheaper than before in comparison to the other good. But then there's also an income effect, which is because you are having a price change, one price goes up, you buy less probably of both goods if one price goes up. And this is so you can decompose every price change into a change of the income and into the price change. Income effect and price effect. And this is what is called Slutsky equation. And I have it here. So now I do it. What happens here? And this is what usually happens, but sometimes it does not. So let's see. So the usual things that happens is the following. We have this budget constraint, 1 over P2, and now we increase P1. So instead of having this P1, here we have P minus P1 prime over P2, and we suppose that P1 prime is larger than P1. The first thing I do is I change the price. Here the price is lower, here the price is higher. So what I do is I change the price and increase the price. What happens is, let's put a solution as we usually will have it, which is here. So before you consume here, and afterwards you consume here. Lower utility, you're always on a lower indifference curve, but you consume less of both goods. So here it's nice because you consume less of both goods. If you consume less of both goods, this is what we have, what will happen normally. There's a normal good and an ordinary good. We can also have sometimes, I can draw pictures where this part is a bit upper to the left and this part is here to the right. So the price of good one increases, but we consume of course more of it, which is called sometimes a given good or an inferior good. Given inferior goods, maybe you've listened. The example which is used in the textbooks is there was a famine in the late 19th century in Ireland. Prices of everything went up, prices of potatoes went up by more than the rest, but people bought more potatoes because potato was still the cheapest food. They couldn't afford the rest, so they switched to the cheapest food available, which is potatoes. A couple of years ago, with the price increases we saw all over the world, with like after the invasion of Russia and the Ukraine, we had prices going up everywhere. People were telling this is due to many companies due to this invasion, but actually it was not. So it seems, as we found out, economists found out all over the world that firms just increase prices. And so it was just an effect like this. So people were switching to inferior goods because all the prices go up. So people were buying more, even if the price increased by relatively more like these white goods in the supermarket. So like what is it, like pasta, spaghettis of the label of the supermarket. Usually these brands, these white brands, which are the brands which the supermarket produces itself, they are affected more by these price increases. Because usually they sell very close to the production cost, to the marginal cost. So if all ingredients increase the price, they have to increase the price more or less by how much the ingredients go up. Brand labels, But Hitler, for example, they have a higher profit margin. So for them, the ingredients, the cost of the ingredients increases in the same amount as for the white brand in the supermarket, but they have a higher profit margin, so they can absorb part of this price increase, so their prices will increase by relatively less most of the time. So the white brands, these very like low quality or relatively like price cost, like where the price is close to the cost of production cost. So in relative terms, this will increase more in the price. Yet people switch. Since prices go up for everything, so people switch from buying brand labels and buy more of these white brands because they are still relatively cheaper than the brand labels. And this you could observe a lot. So the supermarkets all over the world, people are buying more of their own brands of supermarkets because they are cheaper and less of brand labels. And especially by things which are like where you cannot tell a big difference, pasta or rice or whatever. These basic goods, washing liquid, which Ariel was increasing by a lot, some people switch to the white. So these are the things where people are substituting to. And this is when you have price increases, maybe by both goods, but even by one good, which is the white brand in the supermarket, increases by more than the other brands, and people buy yet afterwards more of this white brand goods than before. So you can get this. And what we do in general, so this is something which actually, so there are consultancies which are like price consultancies, which are like economic consultancies, which work a lot on with pricing. And so you analyze what happens, how people change their behavior if you change the prices, and they are interested in this and they know exactly what's going on.
Perfect. May I ask a question?
Yeah.
I always had a question like, and how do economists in practice do a separation between the effect of the substitution effect and the price effect?
How they do it in reality?
Yeah, like in R or whatever, in Python with
Okay.
the database.
So what you can do is, basically you separate the two things. Namely, once you see what happens, how people change their behavior if you change, if prices change. If prices change, what you get is like the total effect in some sense.
Mm-hmm.
The total effect is both together, income effect and substitution effect.
Uh-huh.
But sometimes you can see if relative prices change, so you change the relationship between two goods, prices go up in the same percentage, but relative prices are different. So then you see substitution effect. And sometimes you get like these experiments when income of people changes. And again, so my income goes up this year, university increased by 3%, another guy by 2%, maybe 5% in Pamplona, so you cannot really observe it. But when you can check for income changes for everybody is when, for example, the government changes taxes. If the government changes taxes, this affects everybody in the same way, basically. And like this, or value-added tax, stuff like this. Then you can observe how people change their behavior. This is how you do it. Like you do this natural experiment where you can disentangle a bit the effect of a price change from an income change.
Really interesting.
Yep. So here we get this. So we consume less of those goods, price change afterwards. And now what we do formally, so we go back to the math for 10, 15, 20 more minutes, then we are done for today. So what we do is the relationship between the Hicks demand function. So if I change the price of good K, how does this affect the demand for good L? Price of good K changes, how does this affect the price of the quantity demanded of good L? This was a Hicksian demand, and this is price K. In the end, what I can do is, I can also put L and L here, so K may be the same as L. To distinguish, I put it different. HL, Hicksian demand for good L, price K changes, how does this affect this demand? It would be one good and the other demand. This is equal to the change in the vibration demand when pK changes. And this basically is the substitution effect plus the income effect, which is XL, because the price here is in the P, but also in the W. Okay? So PK is here. In XL, you have it here as a PK, and in W, so I have to do it again. Second derivative with respect to W times XK PW. This is the income effect. Okay? You have substitution effect and income effect. and this is the total effect of the change in the Higksian demand when the price of good K changes. And graphically, like to get an idea, the quantity demanded here, Q, of the good, and here's the price. And then I have two demands of one type and one of the other. This is XPW.
Marcus?
Yeah.
Income effect was the second part, right?
Yeah,
Okay.
because we have W here, income effect. So here and here. And so this is a valuation demand function. So if you change prices, you continuously move on the valuation demand. But for the Higksian demand functions, because for different prices, you obtain different utility levels, you have a jump. This is a utility level 1, and this is a Higksian demand for the utility level 0. You have different utility, and the quantity in both cases, so here it's this one, this is 0. And so what we did is we increased the price of a good from P0 to 1, increase. The quantity demanded goes down. Q0, quantity demanded goes down to Q1. And the utility level goes down from U0 to U1. So this is a relationship between the Higksian and the valuation demand function. So if I change the price, I move on the valuation demand function. But for the Higksian demand function, since I get a different level, the utility changes, so I jump from one Higksian demand to another. This is how they are related. So this is this part here. Now I want to show you. So most of the times you don't, I don't think you don't need it a lot, but there's one way, and this is why I show you how this is related. And this is a picture which is also like this in Masculine, but I'm happy to draw it on the board, because this is one of the few things which you need to memorize. So the subjects, in this master probably not so much, in other masters where you just have to learn 40 pages by heart. Here for your math exam you need by heart, you need to know 3 pages at most. The rest you need to understand, which is good because, well, I always say to my undergrad students, I tell we are economists, so we are lazy and efficient. We don't want to memorize stuff, we want to understand it. Understanding is easier because you sit down, understand it, and you know it forever. And you don't need to memorize it, but you go to the exam, you have your stuff in your head, you know it, you know how to do it, you invoke your skills and you apply it. If you need to memorize stuff, you need to do the effort to memorize everything and have it in your mind, and this is more difficult from my point of view. And probably from yours as well, because you do a master in economics. You go to the law faculty, people will tell you, no, memorizing is better. There's a different approach. And this is one of the few things which I will recommend you to have in mind. So this is one of the things that you understand it, you know it, or you memorize it. Very few things which you need constantly to memorize. And this will be a picture where I put here utility maximization and expenditure minimization on the right, left utility maximization. On the right is expenditure minimization. And then I will relate the two. I will show how one thing is related to the other. This is why I also did this explanation here, to show you the two obviously are related, because expenditure maximization and utility minimization, expenditure minimization and utility maximization should give you the same, which you see from the picture, but it depends a bit how they are related. Now you understand the detail. What maximizing utility, null subject, use the axis, max u of x, subject to px is equal to w. Here we have expenditure minimization, minimize px again by choosing the x, subject to u of x equal to some u of. Okay, this is what we do. Then what we get here? Here we get the valuation demands. XPW, and here you get the Higgs demands. HPU. Well, this we know, we just did. Now, how they are related? Well, you can go from this one to this one, and from this one to this one by substituting utility with. We substitute the utility with VPM. U upper bar with VPW, sorry. Then you get to the vibration demands. And the other way around, you substitute the W with the expenditure function and you get the Higgs demands. Substitute W with EPU. Okay, so you get to the Higgs demand. So again, in some sense, to be able to go from here to here, you have to do all this and then get the indirect utility function. It's not yet a big time saver, but okay, this is how they are related. So once you have the indirect utility function, by going to the next step, plugging these XPWs into the utility function, plug the VPW in here, you get back the vibration demands. Or get the expenditure function, which is the next step here, plugging the Higgs demands in the budget constraint, gives you the expenditure function. If you plug then the expenditure function in here, you get the Higgs demands. Okay, so this is the relationship. Okay, so substitute into W equals Px. You substitute it in here, and what you get is the expenditure function. That is very simple. Substitute it as we just H. Okay, so you substitute the H into the budget constraint, and you get the expenditure function. Now, how can you go from the expenditure function to the HPUs? And this is called Shepard's lemma. And this is one of the things which is interesting. Shepard's lemma is another economist, Shepard. What he showed is where if you take the derivative of the expenditure function with respect to the price J, then you get back HJPU. Okay, which again is not surprising, because you have here the list of XPs. We're plugging the HPUs. If you take the derivative with respect to the price, you get back the group. One to the demand of the group. You can read it, you can read it.
No, that is impossible.
And into W equals PH, and what is into
Substitute it to W.
That one is done.
Into W equals P times H P E. Now, you have this picture also in masculine. You have the same picture in masculine.
So it's P times K PU, right?
H.
P times Higgs demand.
H. Okay, here's the block. And it's the same, so this is the nice thing. And you can also do the same thing on this side, which is substitute into the utility function. Into U of X, plug in the vibration demands into the utility function, and what you get is the indirect utility function. Function VP of W. Okay? And then, how can we go back from the indirect utility function? This is the main trick which I want to show you. From the indirect utility function, we can obtain the vibration demands by what is called Roy's identity. An economist called Roy who found this out. Roy's identity, going from the indirect utility function to the vibration demands. What we do is we take, so the variation demand xi, p of w, is equal to the derivative of the indirect utility function with respect to pi, and we have a minus in front because this derivative is negative. This is one of the properties which we have. Divided by the derivative of the indirect utility function with respect to w. Okay, so this is the main thing which is important. And then you have, going from one to the other, you just invert the function by inverting the function, by inversion. Okay. So if you solve the indirect utility function VPW, you solve the VPW for W, and instead of W you call it E, and the VU, then you get the expenditure function. And if you solve the expenditure function EPU for U, and call the EW and the UV, then you get the indirect utility function. Okay, you can invert the two and get from one to the other. So what I can do is, I could give you the expenditure function and tell you obtain the variation demands. There are two ways to do it. This one, this one, or inverting and Roy's identity. Two ways to get it. So what I once did in a question, in the exam, I didn't give the students a utility function, but I gave them the indirect utility function. And then they had to solve a question with the utility. So you didn't have to maximize the utility like you usually do. You're always having questions, you maximize utilities, you get the variation demands and you work with them. So what I did is I gave them the indirect utility function and asked them to work with the variation demand function. So what you needed to know is Roy's identity. Go this way. Okay. And then this was a difficult question that year, which means either you knew how to do it or not. The other question very easy. But don't very much. So since I told you about the exam now, I'm ready, and I tell you how it's like, because I already uploaded one of the exams. So you can have a feeling, once you have the first or second problem set, you can have a look at it. So the idea is there will be 90 minutes, 1.5 hours. There will be 3 questions. 2 will be relatively easy, 1 will be difficult. There are 50 points. The best student usually gets 30 something points. And then I'm grading on a curve. So best student gets a 10, and so on.
The exam is graded on a curve? Oh,
Because there are 50 points.
wait.
Best student usually gets 30 something, so it's like a 6.
And if the student is at 25 points.
80% fail. The best student is 25. We will have, so the first thing is that if the best student gets 30 something points, it means it's difficult. And so the easiest thing for most of you, if you don't go for the 10, is just to ignore the difficult question. Find the difficult question, solve the other 2, like this, you would be among the best students in the exam. The second thing is obviously you can collude. Everybody gets a 0, I get grade on my curve. And second, I give you a 0.
Good game theory.
Yeah, this we will do later. This is not an equilibrium. Yes, you'll see later on.
It's an efficient equilibrium point.
You will not end up set. You will not. So professors which try to do this, and yes, it was apparently a professor who told the students, okay, you get, so I grade on the curve, if you all get the same points, you all get the best grade. And students were doing nothing for a long time, but a couple of days before the exam, some students were starting to study because they realized if somebody deviates, they end up being very bad. So it was better than to study and get a good grade, it would like be slightly better than the others. And once one guy starts, everybody starts. And so it's not an equilibrium.
Yeah, it's not agree because everyone may want to
It's like
betray the others and get the best grade. So the equilibrium is everyone studying.
So we can lose it. But you will
It's
see.
like the pressure that's like
We will go and get the end of the video. Good, so this is about, so this is one of the few things I will ask you to remember, because it's very useful. Sometimes it's useful. We will have exercises where we will apply it. Any questions?
Which is more efficient in terms of the way to go from one to the other? It depends on the problem.
Because if you get this one, inverting it and taking the derivative, or first taking the derivative and then inverting it, I don't know. Probably the more efficient one is first to take the derivative, because then you get to one thing which you have to invert. If you invert the entire expenditure function, it's huge. To solve for you is much more difficult than first taking the derivative. It gets much smaller. You have a much smaller expression which then you invert.
Yes.
Because the difficult part is the inversion. You have the picture at Mascolel. Mascolel books has a picture which is exactly this picture, nice. Not like it's
Sí, ya sí.
Can you send that photo?
Yes.
Ah, esa.
Sí, sí.
Sí, él.
Tampoco lo pensé.
You wrote an H again in the funds
what? An edge?
in the derivative of
H.
But another question. You said that okay, I will give you have two ways of doing
If you start here, you go this way.
that way for that one. But you give us indirect utility function.
You can convert EPU, then take the derivative and you end up here. Or you take the derivative of EPU, get HPU, and then invert. Then go in this way.
Okay.
Sure, I uploaded it on the drive of the map.
Okay.
I'm gonna put it as a reminder.
Yeah.
You have no more lectures today, no? You have the seminar and that's it.
Yeah.
Do I need to? No, but I delete it. So see you later in the seminar. And next week on Friday. Next week I think there's, I don't know if you have a lecture before, but we start at 10:30. No? According to the schedule, we start half an hour later.